You should know that for a rigid body that is undergoing a fixed axis rotation or the general plane motion, we cannot simplify it as a particle. Let's continue the discussion for the general plane motion case. In this figure, you have a rigid body at its original position at time equal to t. After some time, the rigid body moves to this position, and you notice that the A and B point here is rotating. Also, the displacement vector B with respect to A here is changed during the process. Let's look at the motion of this rigid body. If you carefully watch the motion, you see the rigid body is translating and rotating at the same time. Let's look at the motion again. This time, you focus at point A. So you see the point A is doing the translation, while the displacement vector here is rotate with respect to point A. So when a rigid body is doing translation and rotation at the same time, we call this motion as general plane motion. We can decompose the general plane motion into two parts. For the first part, let's as the point A doing the translation, and then in this case, the RB/A is follow the translation. So this is the translation. The second component of the general plane motion will be the rotation of the rigid body. So this is the rotation. By performing the translation and rotation, you successfully obtain the final position as the previous case. The complicated motion of the general plane motion like this is difficult to be analyzed because it consists of the translation and rotation simultaneously. Luckily, we can decompose the general plane motion into the translation and then rotation separately in order to obtain the same motion. In this example, we perform the translation at point A first, then we perform the rotation at point B with respect to A. It doesn't matter which point you choose for the translation or rotation. If you want to choose the point B for translation, and then point A for rotation. If you do this, you will also obtain the same motion. If you prefer to use this case, then you need to change the direction for this vector, and it should be the displacement A with respect to B, which is equal to negative direction of the RB/A. In this case, we will choose the point A for the translation and vector AB for the rotation. This setting will be used for the next analysis. First of all, your AB vector here is doing the translation to this position, and the displacement traveled by point A is equal to dRA here. Then the displacement vector B with respect to A is changed during the rotation, and the changes is equal to dRB with respect to A. So what is the displacement for the point B here? To find the displacement of point B, let's look at this triangle. Since these two vectors are parallel, therefore we can obtain the vector here to be dRA. Apply the head to tail method on this triangle, then you will have the dRB here equal to the dRA plus the dRB/A. With that, you should obtain this equation where you have the dRA, which can be obtained during the translation, and then dRB/A, which is due to the rotation. So we can differentiate this equation with respect to time here. Then you should obtain the corresponding velocity. In this case, the point B is rotated with respect to A, and A here is the center of the rotation. Therefore, you know that the velocity for the B here with respect to A will be equal to omega cross R. So R is the radius of B with respect to A. By substitute this formula inside, then you should obtain this answer. By differentiate the velocity with respect to time, Then you can obtain the acceleration B. So this one will change to acceleration at point A. And then for this term, you need to differentiate with respect to omega, give you omega dot, which is the angular acceleration. Then you continue with remaining the omega term here and differentiate the r with respect to time. So dr over dt give you omega cross rb slash a, which is this term. And you should notice that the velocity and the acceleration that you obtain due to the rotation here is same with the formula that you use for the fixed axis rotation. This velocity component is called the tangential velocity, and this is the tangential acceleration. This is the normal acceleration. With that, you success to obtain the velocity and acceleration equation for the general plane motion.